Hey everybody, how's it going? Welcome to Chippy's first ever YouTube live stream. My name is Ali Sivji. I am one of the organizers of Chippy. Really happy y'all can join us. So let's get started. So before we actually do get started with the event, I sort of want to talk about the elephant in the room, which is the COVID-19 situation. Unfortunately, with the way things have gone, events like PyCon have been canceled. A lot of local user groups, such as Chicago Python, we've had to cancel a lot of events. We've really lost a sense of the community we've really grown, worked so hard to grow. So we're really excited to be able to get back on and start streaming events on YouTube. So before we do go on, I want to make everybody aware of our code of conduct. This really applies more to in-person events, but I would still say for things like the YouTube chat or chat on our Slack, all of these guidelines still to apply. So what is Chippy? Chippy, or the Chicago Python Users Group, is a Python-focused group that has been meeting since 2003. It really started off as a small group of Pythonistas meeting in small conference rooms or in the back of a bar. And now it's really grown to become one of the largest Python-focused groups in the world. We're really proud of that. So on top of our monthly meeting that we have on the second Thursday of every month, we also have other initiatives such as our monthly project night. We also have a world-famous mentorship program. There's a few changes happening in that program, so stay tuned for upcoming news for how that's going to get started again. We also have a lot of special interest groups that are focused in on more niche areas of Python. So there's the finance SIG, there's the data SIG, there's this one, which is the WebDev/DevOps SIG, and we also have the special interest groups for algorithms and data structure questions. So normally I'd like to kick it off to our meeting sponsor. This month we were supposed to be at Review Trackers. Unfortunately, we had to postpone our in-person meeting, but we do have two folks from Review Trackers giving a talk about some of the interesting services they're working on over there. So really excited to have them speak later on. Do want to make a couple of housekeeping announcements. On April 9th, we're going to have our main meeting. So that's going to be 2 days from now. We're going to be live streaming again on YouTube. And then next Thursday on April 16th, we're going to try to do a Python project night. So the goal right now is to hold it over Slack. So check it out. We'll see what we can do. There's additional information about both of those events on our meetup page. Where can you find us? We do have a very active Slack workspace. You can join if you go to the link, which is joinchippyslack.herokuapp.com. We're going to be having some conversations around our live streams in the Chippy Tube channel, so please check that out. We're also on Twitter. Our handle is @ChicagoPython. And we do have a website, chippy.org. All the information I talked about, it's all going to be available there. That's enough about me. You didn't really come to hear me talk. We're going to have 3 fantastic speakers tonight. That's why you're all here. So our first talk is going to be by Chris. It's going to be on JSON and Protobufs. Suhas is going to give our next talk on testing with hypothesis. And then finally, Andrew and Joey are going to talk about deep learning models for natural language processing. We're going to take a couple of seconds break while Chris gets set up, and we'll be right back. Thank you. Awesome. So Chris, do you want to take it away? Thank you.
Sure. Hello, everybody. If I'm on right now, my name is Chris Moirano. I'm a back-end software engineer at Numerator. And today I'm going to talk to you guys a bit about JSON and Protobufs, two kind of data encoding schemes that exist. Any code or examples that I go through in this talk will be available on my GitHub, which down here, github.com/hotjarnera/talks. I think this is the only one in there right now. but is titled Protobufs. So the purpose of today's talk is we're just going to talk about these two different data encoding types, JSON, which I'm sure most of you are familiar with, and protocol buffers, which is a fairly new data encoding scheme written by Google in the early 2000s. What we're going to do is take a look at what they look like in their binary forms, or mainly hexadecimal form, touch upon how protocol buffers does its encoding, and compare and discuss their different use cases briefly. So the main outline in this talk, we're going to be talking a lot about binary and hexadecimal, especially when we get into the protocol buffer serialization / deserialization. We're also going to look at what a raw request using JSON and protocol buffers is going to look like on the actual wire. Using Wireshark, that's going to be pure hexadecimal. And then basically just go through an example. So to start things off, go through a quick binary refresher on binary and hex. Hopefully you guys are familiar with it, and hopefully if you're not, this doesn't really confuse you a lot. But so just as a quick refresher, most of us, when we count, we use base 10, as we say. And what that means is we have 10 symbols available to us, 0 through 9. And with binary, we only have 2 symbols available to us. And then with hexadecimal, that's 16 total symbols available to us. And that's 0 through 9. And then once we run out of numbers, we just spill over into letters. And so how counting works with those. So when we do base 10, what we do is we count to 9. So 0, 1, 2, 3 to 9. We're out of symbols now. And so kind of like this mechanical process, now we start and just put a 1 in the next column to our left, and then start counting on the right column again. So that kind of looks like 1, 0, 1, 1, 1, 2, ... We eventually get to 99, and then we're out of symbols in both columns. So we move a 1 over to the next column there. When we do this, we say we're in base 10. So kind of each slot in or column is a power of 10. And so what that kind of means is this column is 10 to the 0, which is 1. So you multiply the number you're looking at, 0 times 1, which gives you 0. This is 10 to the 1, which is 10. This is 10 to the 2, which is 100. Just to bring that back to how that would work. So 10 to the 0 is 1 times 9 is 9, plus 10 to the 1 times 9 is 99. Base 2 is kind of like smaller, so everything is a power of 2 in each slot. So you kind of run out of symbols quickly and have to add into columns. So you start with 0, you go to 1. Now you're out of symbols again, so you have to add a 1 into the next column, which gives you 2. Add a 1 over, which gives you 3. Now you're out of symbols in each column again, which gives you, adding a 1 to the left gives you 4, and it goes on like that. Hexadecimal obviously has more symbols, so you can represent larger numbers in smaller values. So one prime example is FF here, kind of follows the exact same scheme as I mentioned before. FF represents the number 255, but is only 2 symbols, whereas 255 in our base 10 is actually 3 total symbols. Hopefully that didn't confuse you guys. Shouldn't matter as much. Just some vocab that I might be using. Bit is a single byte or binary number, single bit. A byte is a group of 8 bits grouped together. You hear a lot about that in computer science and whatnot. A nibble, which is kind of, I guess, the mnemonic device they added to byte, is half of a byte, which is a group of 4. And the reason I'm bringing this up, when we look at hex, it's especially going to be important when we're looking at protocol buffers and what they look like. You have to quickly translate between the hexadecimal to the binary form. And a quick trick to doing that is typically you'll see hexadecimal grouped as 2 characters together. 2 characters in hexadecimal will represent 1 singular byte. And to quickly translate that into binary, you can separate them. So a nibble of 8 would look like this, so only 4 bits. A nibble, just a reminder, is 1000. This is 2 to the power of 8, or power of 3, which gives us 8. B, which is 11, is this nibble, 1101. And together, if you jam those bits together, we get the total number 139. And just to do the quick power of 2 math for you guys, 2 to the 0 times 1 is 1. 2 to the 1 times 1 is 2. You have a 0 here. 2 to the 8 times, or sorry, 2 to the 3 times 1 is 8. And then this last one is 128. So 2 to the power of 0, 1, 2, 3, 4, 5, 6, 7. So 2 to the power of 7. Might be off on that math, but hopefully you guys get the gist of that. So moving right along, we're going to look at JSON. It's basically a ubiquitous method on the web for serializing objects. I'm guessing a lot of you have seen it. Built in it, JSON to start stands for JavaScript Object Notation. So it kind of mimics the what a JavaScript object might look like if you write it by hand. But it is a way to encode data, and you'll see it a lot in JavaScript, or you might use it in your programs to share data between things. So one thing to note about it is schemaless, and what I mean, at least in terms of this talk, is that there's no real defined structure to it. You can put fields in any really order. If you give it the number, so for example, 200, it's just the number 200. If you fall into any other programming languages, you don't know if that's like an integer or it's a long. Similarly, you can give it decimal values, so you wouldn't be able to tell if 2.0 is meant to be like the double value or the float value. JSON natively does not convey anything about the data. It kind of just gives you the data. With JSON, we can represent strings, numbers, arrays, or lists, true, false, null, and then objects or other JSON objects. So just kind of like nesting objects within each of themselves. The main benefit of JSON, as you guys probably all know, is it's super readable. Like it's easy to grasp what this data structure, this is the example data structure we'll be using through this whole talk, is trying to convey. This, sorry, should read ID. So this is saying this thing has an ID of 200. It's holding an array of numbers, therefore, and then it has a nested other object in it, which also has an ID of 2. Pretty straightforward. That's the beauty of JSON. It's easy for even beginners to grasp right away. Another nice thing about JSON is there's a native package, so built into Python, that handles JSON. JSON really kind of mimics, or sorry, not mimics, but looks very similar to what we see in Python as dictionaries. So we can create a JSON object out of this dictionary fairly simple. So ID, defining a dictionary with an ID of 100, an array 1, 2, 3, 4, and another object, which is a sub-dictionary in it. With JSON, we can easily serialize that using json.dumps. Again, JSON is the package built into Python, which when we dump it, will yield back kind of like a string representation of that dictionary. But this is what JSON essentially is. When you send a message to it, it looks exactly like this. It ties very closely with Python dictionaries, which is super nice. Before I move on, does anybody have any questions? I can't really see the question chat, so.
Yeah, checking the chat. I think we're good right now. It's been good so far.
Cool. So I'm going to move right along into protocol buffers, which is Google's way of serialization. They're called protocol buffers. People refer them to as protobufs for short. It's another mechanism for serializing data. So JSON is a way to serialize data. It kind of turns it into that string representation that I showed before. It was developed by Google in the early 2000s, I think in the late 90s, like internally. What's really nice about it is it has schema. So you can define something as an integer type, and when you send that message over, the thing that tries to read the protocol buffer will know that the thing is an integer. It ties in, you have to put things in certain orders. It can represent a wide variety of types, as well as similar to JSON, you can nest protocol buffer objects. They're called messages. We'll see that in a bit within each other. The main benefit is that they are language interoperability. They have interoperability, and what that means is that you can send a protocol buffer from Python, let's say, to a program written in C, and it'll be able to understand the typing and the schema of the Python message that was sent over. JSON, obviously you can do that, but as I mentioned, there's no way to determine for a C program to know if something's afloat as 2.0, or a Python program knowing that. But with protocol buffers, you're able to do that. There's built-in rules for that. One of its main drawbacks is it's really not human readable, but we're actually going to try and read a protocol buffer in this talk. So using it in Python, before we can jump into using it in Python, there's a few things you have to install. We'll get into that in a sec. But everything in protocol buffer, as I mentioned, is what's called a message. And this is basically a data structure, or the main data structure of protocol buffers. You define it in a separate file. Typically, those are prefixed with the .proto extension. You can do whatever you want, honestly, just as long as you hit it correctly with your compiler, which we'll get into in a second. And then once you define the message, you use Google's protocol buffer compiler to compile the message into your target language. So it generates a lot of code for you, which is great. You don't really have to do much, just kind of plug and play with it. And in Python's case, it's going to generate classes or objects for us that we can use to serialize and deserialize data that we may read. So just quickly to go over what a protocol buffer file would look like. This is basically just a copy paste out of a file that I generated. It mimics this data structure I've been talking about in this talk. Some key things to note. So messages are defined like this. Simple message, this is the name given to it. And then your Python, when you compile it, will give you an object called simple message. It does it in camel case. That's just what they recommend in their documentation. You can define it any way you want, to be honest. Really important things to know, as I mentioned, it has schema, so you have to give everything a type. There's multiple types, int32. There's int64, there's strings. You can give arrays. Arrays are repeated objects. And then you can also define other objects. You can nest them, you can put them anywhere else. You can even recursively define objects or fields within it. So a field, basically, just to sum it all up, is type, the name you're giving it, and then the position is the last thing. Position is really important because it's crucial for deserializing these objects, or kind of reading them from when they're serialized back into your program. So cool. So using the protocol buffer in Python, Google has their package on PyPy. I think I found the easiest way, at least for Python, is to install it through pip and then using it as a Python module. If you guys check out my repo, I have just like a compile.txt file. So if you want to play around with it, this is basically just a copy of this command, which I'll talk through in a second. So if you install it through the Python package index through pip, then we can utilize it through Python as a module. So the syntax for doing that is Python, whichever version you're using, calling the module grcp tools.protoc, flag.i. So proto files can import other proto files. So I is kind of your import path. So look for other proto files here, something refers to it. And then in terms of Python, you can, you give it this Python out. I use the period here because that means compile it to this directory. You're basically telling it where to put these Python files it's generating. And then lastly, you give it your proto file name. So it'll compile it for you. One thing to note, that if you install through Python, there's many other language versions. So you can say here, for example, C++ out, CPP out. You can say Go out. There's, I believe, a plugin for Swift, excuse me. And many other languages that they support. They support a wide array of them. I'm not going to go through the demo of compiling. It's just as simple as this. Would take my word for it. So once you have compiled the file, it's going to generate, as I mentioned, this Python file. In our case, it's typically, so let me swing back. I called mine messages.proto. So the compiling is going to call it messages_pb2. It prefixes with protobuffer2. I'm not sure why it does it too. I think it's just an old hangover from when they did protobuffer3. Just to flip back, sorry. They're currently on protobuffer type 3, which is the most up-to-date version of the compiling. They suggest using it. But this encoding schema is extremely backwards compatible. It's one of its main benefits too. So depending on whatever version, you're not going to break a program that compiles something in protocol 2 versions. But that's just this main side point. So back to how to use it in Python. We'd import it from that file. So messages_pb2, import simple message. This is the object, Python object it generated for us in the file. And its serialization is very easy. That is feeding the data you've defined into this object they've generated for you. In this case, I've done the same thing as our JSON message. just made a dictionary and unpacked the dictionary as the initialization arguments. Also supports, on that it supports keyword arguments as well as positional arguments, because as I mentioned, protocol buffers have these certain field numbers that have to be there. So to actually serialize the message, the object has this function built in called serialize to string, which is going to give a binary string output. So in our case, that's this representation here. These are all hexadecimal bytes that represent the message structure. So if we compare that to what our JSON looks like, we can see that protocol buffers are just inherently much, much smaller. So on the left, this is the message we defined, and then this is the actual output in bytes set with whatever field it's setting. Our previous message here. So ID 200, an array of 4 things, and then a nested object. This is a total of 14 bytes. And then again, a huge benefit, we know that it's going to be an integer of size 32. So if you give that to C, which has to define an integer of size 32, it's going to be able to work there. If we take a look at JSON, we kind of see a bunch of bytes. And what do these actually represent? We'll get into what the protobuf ones represent because they're much smaller, so it's a little trickier. But the JSON one is pretty straightforward. These bytes, if I'm going to hop, are just the string representation of this JSON data structure. So 7b, if you look at an ASCII table, is this opening brace. 22 is this quote. 69 is the I. 64 is the D. This is 22, another quote. 3a, a colon. There's a space, which is 20, and then 32 is the number 2 as a string or a character, an ASCII character. 30 are zeros. So obviously that kind of gets expensive because you have to put everything, every character represents a single byte. So this JSON data structure encoded, if we send it over the wire, is going to be 60 bytes, much larger than our protocol buffer version. So with that, let's take a look at deserializing the actual protocol buffer. So it generated this weird string of bytes. How does the computer interpret it? Like, it'd be crazy if you had to hand interpret this all the time. Before I move into that, is there any questions?
Looks like no questions. Just to make everybody aware, if you do have questions, please ask them in the chat and we can get the speakers to answer them. But yeah, I think we're good for now. Thank you.
Cool. So protocol buffers themselves are basically just key value pairs where the keys kind of convey a lot of information. And by a lot, basically like 2 things. They give you the type of the key that you need to read next, as well as the position. And the way it's able to make things much smaller is through another serializing way of numbers called varants, or variable integers, I guess, is how that is expanded. And so what variable integers do, they kind of like, if you think about a number, if for any of you who are familiar with other languages or like C, for example, if you define an integer in C, it's 32 bits no matter what. So you give the number 1, as we saw in binary, the number 1 is a single bit, right? Why do we need 32 bits to represent that in C? That's just the nature of the language. That's very oversimplifying it, but varants are a way of encoding these small numbers into smaller packages and conveying that how much data you actually need to read. So one crucial thing, varants are usually groups of bytes together. And if any of you guys are familiar with floating point numbers, you can kind of think of like the most significant bit or the leftmost bit in your byte as a flag for a negative number in floating, or sorry, not floating point, but negative numbers, excuse me. So varants use the most significant bit again as a flag. And so the rules that are set there, if the most significant bit is set as 1, that means this byte, singular byte, is part of a larger group, because obviously you can't represent huge numbers in just a single byte. That'd be nearly impossible, or it is impossible. So 1 as the most significant bit of a byte means that this byte is part of a larger group. When you encounter a 0, that means it's the final byte of the group. You can see bytes on their own, as we will see. That means it's the only part of the group. So just to get that into a concrete example, let's take a look at, excuse me, our deserializing our protocol buffer message, which is up here. So we're taking a look at the first byte here. Since it's just a message on its own, we're expecting a key, right? So the first thing we need to do is we know keys, as I mentioned in the last slide, are variable integers or varants by default. So we first break this key down into binary, right? So 08 into binary looks like this. The hexadecimal representation, that is, looks like this. And then this is representing our ID is equal to 200 or an int 32. So the first thing we notice is that the most significant bit here is set as 0. So that means it's the only byte a part of its group. So we can ignore it. The next thing we can garner from this is what type this key is. On the right-hand side here, also on Google's documentation, is what the numbers represent as types. So in our case, a varant is type 0. 64-bit is 1. Those are fixed in size, so you're always going to get 64 for bit. Length delimited is something like an array or a list, if you will. Start group and end group, these are old protocol buffer language schema. It's deprecated, but has to be there for backwards compatibility. And then lastly, 5 is the 32-bit fixed in size. The way it's defined is that the lower 3 bits, so these 3 bits of our group number, tell us what the type is. We have 3 bits here, which you can technically represent as the number 7 if all ones are set, which leaves maybe they'll add 2 different types in the future, but who knows. So anyway, in our case, the lower 3 bits here are set as 0. So you kind of ignore everything to the left of this and then use these 3 to determine what type it is. In our case, it's 0, which is a varant. Varants check int 32, int 64, uint 32, which means unsigned, means only positive numbers. Signed int 32, which I believe is the exact same thing as int 32. Same with 64. Bools, so trues and false, and then enums, which is another part of the language, but are technically just integers on themselves. So from this, again, we can see we're dealing with the next number, so 8 being our key. So the next thing we're going to be looking for is a varant. That's what this is conveying to us. Next, what's also encoded in the key is the field number. And the field number is also encoded in the message by basically right shifting our number after we determined the type. And so, as we said, the lower 3 bits were used only to get the type. So now we don't need them anymore. So now if we right shift our number, we get the field number out of that. And that's 1. One thing to note here too, these most significant bits wouldn't count in the shift. It would be like shifting a 7 or a group of 7 bits over. But so this leftover binary after the shift gives us 1. So we know it's the first field number. So just from this singular 8 hexadecimal byte, we were able to garner int 32, the type, as well as the position that it's going to be in. So now that we know that, the next thing we can do is actually grab our value. So next we need to know, as we saw before, the key is going to be a varant. So now we're looking for a varant. So we take a look at the next byte, which is C8 in our case. So broken down into binary that looks like this, 11001000. And the thing to note is that in this case, the most significant bit is actually set. So this has to be part of a bigger group of bytes. So we have to bring in the next byte as well when we're determining this number. So we see here again, most significant bit of C8 is set, but now we have 0, 1, which is actually set. So cool, we know that. We know this group of 2 bytes is going to represent the number 200 somehow. This is the number we're looking for. So how is it going to do that? Clearly in the binary, so 0, 1 in 1 byte, and then this much over is going to be 256, 512, 1024, blah, blah, blah. It's going to be a much larger number than 200, clearly. So how does protocol buffers figure this out? So when dealing with a WAR end, again, as I've always mentioned, you ignore the most significant bits, and now you're left with these 2 groups of 7 bits, so 14 total bits. Varins store the actual number you're looking at in what's called reverse order, or little endian, if you will. So what we need to do is essentially take this group of 7 bits and stick it on the front of this group of 7 bits, which yields us this number in binary, 11001000, which I've omitted these big groups of zeros in front because they're actually not needed, which this actually gives us the number 200. So this is 8, and then this is 3264 plus 128 plus 8 is equal to 200. So that's how it's able to represent this number 200 in a smaller group of bits. Obviously, you kind of lose some efficiency because you're wasting these bits, but they're absolutely needed for determining how big group sizes are. So as you can see, 14 bits to represent the number 200 is a lot smaller than something you'd see in another programming language where, your integer of size 32 would be 32 bits big. We're able to convey 32 total bits in only 8 bits, really, which is kind of cool. And if you have a question as to how it's able to bring it out into an integer 32, well, the protocol buffer file defines it as an int 32. So obviously when it deserializes it, it would take the number it read, 200, and then expand that out for the typing of whatever language you're using. So the next quick example we're going to look at is how it is able to represent arrays. And so in our case, our array is as well numbers. So we're going to be dealing with varins again, but it is a different type. So we'll take a look at that. First things first, we'll just quickly run through. We're repeated int. So repeated is length delimited. So for example, when you have a list of 10 elements, you need to somehow convey that there's 10 elements coming ahead. So we still have to use the key. We still have to use the typing. And there's a little extra information given with it. So using what we used before, we first see that 1, 2 broken into binary has its most significant bit set to 0. So it's the only group in its byte. We're looking at the lower 3 bits, which gives us the number 2 in binary, and that tells us that the type is length delimited. And then when we right shift this number over, we get this binary number, which is 2. So we know that that is the second position. So repeated elements are a little different. So when you're deserializing it, the next byte, so in our case, we're looking at 1, 2. The next byte is going to be 0, 5. That's going to be the number of bytes we need to read ahead forward. Again, these things are variable, so you have to somehow convey the number that's going to be ahead. And I do believe that this number itself is a variable integer itself. So if you had a number like, I have a list of 10,000 things, it's not going to be some huge 32-bit number to represent 2000. It itself will be a variable integer. So in our case, 0, 5 didn't really break it into binary, but it's pretty simple. 0, 5 is just 5. So this is telling us there's going to be 5 bytes ahead of us. That is these 5 bytes. Again, we saw that it was going to be repeated. And this, after the repeated, the int32 is going to tell us, hey, this is varins following us. So we have 5 bytes to represent these numbers. So we break these down, 0, 1, 0, 2, pretty much standard. Don't really have to do anything because these are variants, but their most significant bit is set to 0. So there's no shifting or appending that you have to really do to get those. But the last one, 2 bytes, 9003, is going to represent the number 400. And like similar to we saw with the ID, most significant bit of 09 is set. This byte is not. So we take these 7 bytes, stick them on the front of these 7 bytes. That gives us this binary number, which is 9 bits to represent the number 400. And then lastly, just want to quickly touch upon if you have nested objects. So nested objects in themselves, our object that we defined in the protocol buffer file was just an object right here with one ID field that was of int32. So when we take a look at these next group of bytes, these group of bytes actually represent an entire object on their own. It's by default length delimited because you don't know how big the nested object's going to be. So we have to break it down, and then fitting inside this little group of bytes is going to be length delimited information as well as the object itself, as it were on its own. So just quickly running through this, we can see we have 1A is our first byte, of this object group. 0 most significant bit sets. We don't have to look at anything else. Its type is going to be of 2, length delimited. So we know the next byte is going to represent what we have to read next. It is in fact the third field as we defined it. So now looking, we see there's 2 more bytes we need to read, but what do those represent? And then finally, it looks very similar to our first byte. We have an ID that is of int 32, and that is going to be 08 is going to be the first field, similar to our first field, and then 02 is the number 2, as we defined, in our case, our other object. I'm not going to flip back, but that was exactly the number 2 that we set. So before I move on, I'm just going to go into a quick demo. What we're going to do is I'm going to open up a Wireshark session for if anybody's familiar with that, which basically allows us to snoop on requests. In my case, on my network, it's going to show the bytes. I'm going to send a HTTP request using this example, both in JSON and then in protocol buffers. HTTP is going to be for JSON, and then for protocol buffers, I'll use RPCs, or remote procedure calls, that kind of becoming popular, using Google's remote procedure call library. Then we'll get a feel of what the actual like payload, or like what is actually sent over the wire on my network over. So before I jump into that, does anybody have any questions? I can actually flip over and see now. No, I can't.
Also, there is one question, but it's around like Python implementation. I think we can get to that at the end.
Sure, totally. I totally just lost my thing. My slides, that is. Okay, cool. So just to quickly show you, I have this basic server set up. These are all copied over. I'm running the servers, 2 instances of them. One's running gRPC, one's running HTTP. They're running on a Raspberry Pi at my house. So it's on a different computer. So we're gonna get a bounce message back. Basically just what I'm doing is making a JSON payload, sending it over with requests and posting to my server. That'll make it easier to find for us. And then same thing with gRPC, just sending the message over. It's a little more complicated with gRPC, but we're going to send it over.
A little bit bigger?
Ooh, sorry. Yeah, totally.
Thank you.
Maybe I can't. I can't, but I can use Sublime and do that. Oops, sorry guys. Whoops. Bear with me here. So this should be bigger. So this is basically, I'm just sending a client over, or this is just a basic client, which is going to send a JSON version of our payload, the thing we were talking about in our example. It's going to post it to my server. We're going to be able to snoop on it with Wireshark. Similarly, this is going to do it with gRPC, which is more tailored for protocol buffers. HTTP isn't really that tailored for it. I can explain why in a little bit. If anybody has questions on why not, we're kind of out of the scope. But anyway, it's going to just send over the exact same message, but in my case, simple message goes in a request object that I defined differently. So without further ado, let's take a look at Wireshark. For anybody, sorry, this is kind of small. It's going to get bigger when I can't really make it bigger, but if you can look closely, I'm basically going to be looking at everything that's coming over my Wi-Fi adapter in my computer, coming through it. So things it sends as well as things that come back to it. But I'm going to filter it down to the host. This is what the static IP of my Raspberry Pi on my local network. And then my HTTP server is going to be running on port 888. And then the gRPC one is going to be running on port 50,051. So what we see here is just kind of, I've filtered it. There are packets flying around. You're just not going to be able to see them, but my 2 servers are running on my Raspberry Pi here, as we can see. So I'm just going to call my client, which is, we got a JSON response, so 200, and then I just sent back a blank message. So if we flip back over to Wireshark, let me drop this down a little bit. So basically what you're seeing here are all the HTTP handshakes or TCP handshakes that are going on when my client program was trying to talk to my Raspberry Pi. I structured it in a way where the first one was going to send the JSON, sleep for a few seconds, and the bottom one is going to be snooping on my gRPC one, which looks a little different. It's because it's not an HTTP request. It actually uses HTTP 2, but it's for a different session if we wanted to talk about gRPC. So as we can see, here's my post, which is the content type application JSON. And if we peer into it, bring up these. So this is the actual request. These are all the headers on the request, and whatever on the packet is needed by the server. And then down here on the right, we can actually see just as a string, as I mentioned, Wireshark's going to print things in ASCII on the right. It's kind of why you see these weird characters, and sometimes you can't see things. But our JSON thing is, as I mentioned, encoded in ASCII, and here's the big whole thing with it. It's, as I mentioned, I think 68 or something bytes. I don't remember. But it's clearly a big message. So let's pop over and look at the packet that was sent with our protocol buffer. It's a little bit confusing and tougher to find because Wireshark's not that great at finding them. But this is kind of this big gRPC request, or RPC request. It's got, these are all the headers and whatnot. You can see it's HTTP2. But if we look all the way down here, our message, sorry, is this the right one? Yes, it is. Our message started with 08. I can't really find it. That's okay. I promise it's in here. It started with 08, but it's going to just be the bytes that are actually in there. I'm not able to find it. Apologies, guys. 70 2C. These are control characters at the end. But anyway, I promise it's there. Can't really find it. If you guys want me to send you a printout after, just give me a question. But yeah, point being that the actual content body of the message of this gRPC thing is going to be about 14 bytes in total, which is a lot nicer on the network than sending a big JSON response. Don't save. So let me pop back to my slides if I can find them. Escape. Interesting. It's got to be some here somewhere. No. Let me drop out of Chrome real quick just to get.
I think we lost Chris. He will be right back. Just hold on for 1 second. We got some technical difficulties. Yes, well, we're waiting for Chris to get back. Let's start talking a little bit more in the chat. What have y'all been doing during the COVID-19? I have not really been able to leave and do anything, so I've been learning a lot about Kubernetes, moving actually one of the Chippy open source projects called Busy Beaver, which is our open source Slack bot, moving that to Kubernetes. What projects are y'all working on? Would love to hear about that in the comments. Yeah, we got some love for Kubernetes in the chat. How are y'all using Kubernetes? People are doing Vim golf. I like that. If we should actually do a Chippy like addition of Python golf, the least number of characters, least number of lines, or the most Pythonic way of doing something would be a good way to go about it. All right, we got Chris back on, so I'm just going to add him to the broadcast.
Sorry about that.
Hey, Chris. No, it's all good. Do you want to share your screen? We'll get you going again.
Yeah, so I'm just wrapping up here too anyway. Cool. So there we go. Can you guys see me?
Yeah, they can see you.
Okay, cool. And so just the last thing I want to talk about is best cases for using JSON versus protobufs. These are just basically my opinions. JSON itself is probably best suited for the majority of web cases. I mean, it's withstood the test of time. So many guides written on it. So many people are used to it. And for the most cases, you're not going to be sending enormous JSON messages anyway. It's mainly front-end information and stuff like that. It's much more human readable, so it's super easy to debug. And then like your browsers, for example, Chrome has a JavaScript engine built in, Firefox, all of them do at this point in time. And they will be able to interpret JSON. On the other hand, protocol buffers are best used for network communication when you have a backend application or multiple microservices, for example, one written in Python, one written in Go, one written in C++. Protocol buffers give you this easy way to just convey information between those different applications written in different programming languages, allowing them to communicate. If you have, your network costs are a premium, you need to really shrink your messages. There are ways to make JSON messages smaller, but from all the research I've done, I think protocol buffers beat out most of them, if not all of them. And as we always say, it's always best to be nice on the network. Don't hog bandwidth. So protocol buffers, if you really want to be nice, great way to shrink your message bodies. So with that, any questions? This is my personal email. Feel free to shoot me any questions about this talk, anything else, just want to chat, I don't know. Or if you have feedback, this is my first chippy talk, hopefully not my last, so I'd absolutely love feedback on it.
Awesome. Thanks so much for talking about protobufs, Chris. Would like to, we normally do applaud at the end, but being online, it's a little bit difficult. So if you all want to just smash that like button to show Chris that we appreciated his talk. I actually always wanted to say that on YouTube, so I'm really glad I got a chance to do that. Please also, if you have any questions, ask them in the YouTube chat. We do have one question from Nick Lee, just brought it up. So is it more important to use ordered dicts when passing to a compiled protobuf? And that's to avoid the keys from rearranging.
No, it just totally depends. And so for the example that I used, the compiled message, or the thing that they give you in Python, has the ability to, where is that? The object itself, the initialization, has keyword arguments. So it's going to match those keyword arguments to the unpacking of the dictionary. If you were to unpack it differently, I guess in an ordered way, then yes, you would need it. But for the most part, it will accept keyword arguments. So not that important to use an ordered dict in that case. Hopefully that answers your question.
Yeah, awesome. So there is another question from Ryan. What is the performance impact of serializing and deserializing?
I don't have numbers for you, but obviously it's going to be like a CPU intensive, more intensive thing. So yes, it'll be, maybe you'll have smaller packets sent over. So your like network requests will come and go quicker, but the actual deserializing is going to have to be like a CPU intensive operation. It's going to have to figure out what the bits is. From research that I've done, I meant to add some numbers, but apologies that I didn't. I've seen that protocol buffers will beat out JSON in the majority of cases. One caveat would be like you lose size if you just said everything was like a fixed int64 in width and whatnot. But yeah, that's pretty much it. From everything I've seen, it's always faster than JSON.
Okay, awesome. Thanks for answering that. So I don't have this question up in the chat, but I was sort of wondering, like, how are you deploying like web applications or deploying services that are taking advantage of protobufs?
I'm just using it for testing in my own. I don't really have anything like production wise. So my deploying process, if that's what you're asking for, is very manual. So I'll go and compile the thing. If I make any changes, which I typically don't, try and make everything as mature as possible, as fast as possible. Basically just pushing code. If I have to compile it, I'll go in and manually compile the protocol buffer messages themselves.
Oh, while we're waiting for them to clarify, there's a little bit of a delay. Let's talk about like complex data types.
Sure. In protocol buffers or just in general?
Well, yeah, just like what are some of the complex types you can like get in there?
So as I mentioned, like nesting objects in themselves, it's basically built around number, strings, arrays. If we look at, if you guys can still see my screen, I'm totally not sure.
You are not sharing. We can get you back
Okay.
if you need it.
Yeah. Truth is, we'll be adding more schemas or more complex types. I think the native types, at least for as far as messages go, I don't think they're going to be adding. As I talked in the Google tries to make this as backwards compatible as possible. So the typing is really limited to those 3 lower bits in the key. And as of right now, there's 5 taken up, which leaves, sorry, 5, yeah, 5, which leaves 2 more types, because in 3 bits, the highest number you can represent is 0, which leads, sorry, so is 7. And there's 0 through 5 is already taken. So to handle backwards compatibility, I'm guessing the most complex, they can only add 2 more complex types, is the only thing possible, or else they will break their own backwards compatibility and probably have to generate a new type of encoding mechanism.
Okay, awesome. Well, thanks again for giving this talk. If anybody does have any more questions, please feel free to reach out to Chris. He shared his personal contact information. He's also on the Chicago Python Slack. So next up, we're gonna have Suhas talk about hypothesis. Please give us a couple of seconds while we get Suhas all set up. Thank you.
Thanks, everybody.
All right, so next we have Suhas. Do you want to say something, Suhas, just to make sure your volume's working? I think you're muted right now.
Okay, can you hear me now?
Yeah, we can hear you now.
Okay, yeah, I had it muted. Sorry about that.
Okay, awesome. Suhas, do you want to take it away?
Yeah. Hi, everyone. I'm Suhas. I study at Illinois Tech. Yeah, I hope you're all staying safe. I'm stuck indoors preparing for coding interviews. I'm using a book to prepare. Some of you might have heard of it, Cracking the Coding Interview. It has a great selection of problems and good solutions, but test cases. You can find some on GitHub, these test cases, but there really isn't a lot. You would think the quarantine gave me enough time to write all the test cases that I wanted. It did, but I wanted to generate them because I'd almost always miss some obvious cases, and it's nice to have less work. This led me to property-based testing. I'll start with a commonly used example, reversing an array. Now, say instead of manually writing this test, going from 3 to 1 to 1 to 3, I want to generate lists of integers so I can test a broader range. There is a library to do that. We'll come to that later, but how do I test my output now? My first thought was to find a known implementation on the web and compare it to mine. But it sounds hacky and unsatisfying. Instead of this, we can test some properties of the result itself. First, is the resultant string of the same length? If so, we're probably on the right track. Second, we can use the property that reversing the reverse of a string will give us the original back. This captures the intuition behind property-based testing. It was popularized by QuickCheck, a Haskell library. Python 2 has a library called Hypothesis. Hypothesis exposes something called strategies with which you can generate characters, strings, integers, lists, or sets of integers, and many more. You can even combine them the way you like, and you can create a custom strategy. Up next, I'll show you how I generated test data for my coding problems. Okay, so the question is, determine if all characters in a string are unique. In this function, I first create a set, and for every character in the input string, I check to see if it's not in the set. If so, I'll add it to the set. If I encounter a character that is already in the set, that means we have a duplicate, and I return false, else I return true. This is a test function which tests the above code. Here I supply these unique functions with what I already know to be strings with unique characters, and I expect the result to be true. To generate these unique characters, I use hypothesis. It provides a decorator given to which you pass a strategy. Here, we want to generate lists, and the elements of the list are characters. I've specified that I don't want to go beyond the Unicode code point 127 to stay in the ASCII range, and I've blacklisted control characters and surrogates. And I've also specified that the elements in the list should be unique. I tested strings with unique characters, and now I want to test non-unique ones. I generate the tests in a similar way, except that I don't set unique to true, and I use a filter method to weed out randomly generated lists with unique characters. I also have to change the assert statement within the test because my function should now return false. And then I run PyTest like I normally do. I ran into another problem in the book where the test case generation is a bit more involved. So given a string like this, the function should compress it to this string, repeated characters replaced with their counts. The resulting string should be smaller, so this output is invalid and it should just return the original back. Now I need to generate strings with repeated characters. First, I'll specify a strategy to generate the characters that make up the string, which are ASCII letters, and no numbers, which I've included in the blacklist. Hypothesis provides a composite strategy with which you can combine strategies. Here, total characters is a number of characters, each of which I will repeat. I'll arbitrarily determine this number by generating integers, again, using hypothesis. I'll determine the number of times to repeat each character in the exact same way, and then append it to a list. I will then return the string. Okay, so we now have the function to generate repeated characters, which we're using to test a solution to the string compression problem. Assume the compressed string function has been filled out. Also, to test this function, I wrote another one to decode the string. And I'm going to use these three functions to write my test. In the test function, I assert that the input string is equal to compressing it and then expanding it again. So compressing and expanding it should leave the string unchanged. It's similar to what we saw with reverse earlier. This encode decode pattern is pretty common. I don't know how to choose properties before I had read blog posts about it. In one of John Hughes' talks, he talks about how reducing complex data structures to simpler ones can help. I found this very helpful when trying to come up with properties to test linked list problems. Say I have to write a function to remove duplicates from an unsorted linked list. To test this function, I need to pass it a linked list first. But before that, I create an array of integers using hypothesis, convert this array into a linked list, and then pass it to my remove duplicates function. The linked list that is returned can again be converted back into an array. To test the result, I just have to check if the set created from the original list is equal to the set created from the result list. You can see how converting to an array representation can simplify things. It can simplify other problems too, like returning the kth last element from a linked list, determining if the linked list is a palindrome, or partitioning it around a value. Yeah, okay. I think I'll end my talk with that. I've linked some resources that I found useful. I think I went a little bit over. Do we still have time for questions? Or
Yeah,
the encoding string. I can just go back to my slides. Yes, I can. Yeah, you can see this expand string, right? Now, I was testing expand string using unit cases, using examples like B7, B7, but I didn't realize that if I had B10, because 10 was a 2-digit number, that's something I hadn't taken care of at all. And it's something that I only came across while I was using hypothesis. I don't know if that answers the question exactly, but
yeah, no, it definitely does. Like edge cases are hard to find, like test cases are hard to come up with. And I think hypothesis really does do that great job of finding that edge case and simplifying it to like that simple example.
Mm-hmm.
Cool. Let's just wait a couple of seconds for questions to come in.
Also, I don't have the code linked. I'll have that soon up on GitHub. I'm just gonna clean it up and.
Perfect. Would you mind sharing a link on this YouTube video so folks afterwards can find a link to your slides?
Oh yeah, definitely.
Awesome. That'd be great. It doesn't look like any other questions are coming in. Can we give Suhas a round of applause for that fantastic talk? Thank you so much.
All right. Thank you for listening. And yeah, thank you, Chippy, for having me here.
Awesome. So next up, we're going to have Joey and Andrew. Just give us a couple of seconds while they get set up. Thank you. All right, Andrew, got you on. Joey, have you on? And I have a screen sharing on. Awesome. Do you just want to give a shout out on the mic just to make sure everything's working?
Yeah. Can you hear me?
Yeah, I can. Joey?
Oh, yeah, sorry. Am I good?
Okay, perfect. Yeah, we're good to go. Andrew, Joey, take it away.
Sounds good. All right. First of all, thank you everyone for joining us remote today, and to Chippy for organizing this. So this talk is Deep Learning Models for NLP. I'm Andrew Johnson. I'm an NLP data scientist at Review Trackers here in Chicago. So I will be doing the first portion of this presentation before handing it over to my colleague, Joey.
I'm Joey Schuringa. I'm a senior software engineer at Review Trackers. I will be handling more of the implementation aspects in the talk.
All right, so natural language processing, sort of like the title says, processing human language. So I guess I don't know necessarily about the breakdown of the audience listening right now. If you're already decently familiar with NLP, maybe this talk won't be something terribly new to you, but I'd like to introduce it, and especially how state-of-the-art deep learning is used to tackle several NLP tasks in as much detail as possible, given the very, very compressed time frame. But so if I'm trying to explain NLP to someone who's less familiar with it, I like to start off with very salient examples because it does affect our everyday life. I like to say, you know, if you've used Google Translate or Siri or Alexa or something similar, you've already interacted with NLP. And so under the hood of those, you would say like, oh, Google Translate, that's machine translation. That's a major NLP task. It used to be done with statistical models. These days, most state-of-the-art machine translation will be deep learning based. Siri, obviously, there's a bunch of different tasks that sort of come together to make that work. But one example is automatic voice recognition. So like speech to text, similar technology. And Alexa or other similar digital assistants, one component of them would be dialogue generation. And so actually the tasks I'll be going in more detail later in this talk will not be any of these I've listed here, but they still fall under the same umbrella. And so, like I mentioned, how deep learning is used for machine translation, I wanted just to start off by establishing a sort of the distinction between several terms, which some people might be confused about, or some people might think are completely synonymous, when in fact they're related, but they're more hierarchical in nature. So artificial intelligence is basically just making a computer behave in a way that seems intelligent. However you slice and dice that to achieve that goal can still be called artificial intelligence. So even if I, sit down, spend 5 years of my life coding a bunch of like if-else statements, but the outcome seems intelligent, you could say that's AI. But as you sort of go in on this circle chart, it's more specific, your approach to achieving that goal. So machine learning, the keyword there is learning. The idea being you have this data and your algorithm is able to process that data and achieve your task, maybe find patterns in the data. So then within that, there's deep learning, which, so this is leveraging neural networks. So the idea is, it's based off of the neurons in a human brain. So the sort of corresponding part of a neural network would be a node, and those nodes are arranged in layers, which is where you get the term deep. That makes them deep. So it's that sort of common understanding established. Currently, one of the big state-of-the-art models for NLP is BERT. That's an abbreviation for, it's quite a mouthful, bidirectional encoder representations of transformers. Won't get into that, but sort of the big thing right before BERT was actually called Elmo. So you see NLP for some reason recently has a big Sesame Street vibe going. But BERT is from Google AI, came out about maybe a year and a half ago. And it sort of does several things very well, which is why a lot of people have been using it. One thing is that it's pre-trained on just massive amounts of data. So, again, deep learning requires training data. And if I have some task I want to achieve, getting all that data for my task to train a model from the ground up takes a lot of time, takes a lot of data. BERT, by nature of being pre-trained, you don't need as much to get it going. So maybe it already has this base knowledge of the language and the task, and then I just toss in a little bit of my own data to, they would call fine-tune it. So that's a big benefit. And then it's also quite easy to use for multiple tasks. So maybe whereas before you would have quite different architectures from one NLP task to another, BERT BERT itself is the majority of your architecture for these various tasks, where all you need to do is maybe add one layer at the end to make it work for that specific task. So it's almost like BERT has given you this nice, big, delicious chocolate cake, and you just have to decide whether you're going to put a cherry on top or a strawberry or some whipped cream, you could say. And then I just wanted to highlight the performance of BERT and similar models. This is the GLUE leaderboard. So it's updated. Well, let me explain it. So these are all various different NLP tasks and different models' performance on them. But this is sort of the average score across all of their tasks. So you can see Albert, that's derivative of BERT. StructBERT is like BERT. T5 is also Google AI, so that's sort of building upon their BERT model. Roberta is from BERT. So, and actually Ernie and like Electra, those could be similar to BERT for all I know. They're just, I'm not familiar with them because this is updated as new models come in. But I'm just trying to highlight that BERT and related models are really just dominating these various NLP tasks. And you'll see that us mere mortals are only ranked 12th. So that might seem kind of like, I don't know, maybe jaw-dropping that all these models are beating human performance. But with that in mind, they did sort of update some of the tasks to make them more difficult for machines compared to humans. So the SuperGLUE leaderboard, which is newer, at least for the time being, humans are still #1 on that. So moving on. I also just wanted to toss in a slide where someone who maybe wants to get into NLP or deep learning but doesn't know sort of libraries to use or where to start, maybe these would be some references. So you might already be familiar, but Python has a sort of a nice array of machine learning libraries right off the bat. PyTorch is fairly easy to get into. TensorFlow is used widely. Before it was TensorFlow 1.0, which you could argue is kind of more difficult to get into because it sort of builds a symbolic graph and then executes it. But TensorFlow 2.0 has eager execution, so it might be more intuitive for some to use. Keras these days can kind of come packaged together with TensorFlow, so it's easy to use Keras if you already know TensorFlow. And then there's MXNet, which I've used a bit as well. Personally, I'm not as big a fan of it, but it's sort of like Amazon's baby. It's their machine learning library. So then for BERT itself, I would highly recommend Hugging Face. They've got implementation of not just BERT itself, but all these other models, Roberta, Albert, not just in English, but all these different languages, well documented. So I would recommend Hugging Face's implementation of BERT, which is through PyTorch. And just some other things if you're not familiar. Spacey is great for a lot of different NLP tasks. It's fairly easy to use and it's pretty efficient. So like maybe I have a string that's just a long sentence. I could use Spacey to automatically break it up into different sentences, different words. I could get the part of speech of those words. I could lemmatize those words. So like I could, normalize running to run or like went to go. All of that can be done very quickly, easily with Spacey. And then scikit-learn, that's great for other machine learning tasks, dimensionality reduction, clustering, what have you. So just wanted to sort of lay that out there. So then I would like to go over how you might use BERT for some NLP tasks. That's kind of weird. You're supposed to be seeing an image here. I don't know what happened, but that's not a huge deal. Basically, just imagine here there's a box that says BERT, more or less. So for one NLP task is named entity recognition. And when I first was introduced to the task, it sounded kind of boring or not that important, but I just wasn't appreciating how actually prevalent it is. So I'd like to start off with an example of, let's say you have Google Home or a similar device. You want to be able to tell that device, play Hangman versus play jazz versus play the Smiths. So, in one case, Hangman is a game, jazz is a genre, the Smiths are a band. So it needs to be able to recognize that distinction. And so this example here, it's got play, rock, and the image would have like ... So you have the rest of your tokens, and then maybe the final token is please. So for every token, it needs to predict across your entire tag set. So maybe our tag set, let's say, is game or genre or band or O for other. So it's not a named entity at all. So ideally, our model will say, okay, for play, the most likely tag is other, rock, and roll. Each of those tokens should be predicted as genre. And there's a little bit more nuance that goes into most NER systems in that you want to be able to distinguish rock and roll, where each of them are 3 separate named entities that are a genre, versus rock and roll, they should all be combined. Rock and roll itself is one named entity, but that's just sort of a little subtlety with the tagging system. But so that's named entity sort of in a nutshell. And so you have your BERT layer, which takes in the text at the bottom, and then you just have this layer at the end to predict over every token. Now, another task is classification. So maybe we have a sentence, great burgers, ... milkshakes. So like maybe it's great burgers and wonderful milkshakes. So here what we're saying is, this input, this entire sentence, refers to the topic of food as opposed to, say, service or value or what have you. So the difference here is that instead of running this prediction over our tag set for every individual token, we're only running it like once for that utterance or sentence, whatever our input is. So this whole thing, great burgers and wonderful milkshakes, should be classified as food. And then the third task I'd like to introduce is sentiment analysis, which actually in this example is basically the same under the hood, just your tag set is now positive, negative, maybe you could have neutral as well. So again, great burgers and wonderful milkshakes, that should be predicted to be positive. So what that really has is 2 different BERT architectures, or BERT with sort of 2 different applications, the sequence labeling and then the sort of classification approach. I should point out, though, that if you're just going to use this approach that I outlined for sentiment analysis or classification, there would be some error modes, or at least depending on what input you'd expect. So I just wanted to acknowledge that if you had input that says something like great burgers, but the service was very slow, already you're running into some difficulties because, one, that's 2 different sentiments. Burger is positive sentiment, service is negative sentiment. So if you're looking at that entire input and trying to say this whole thing is positive or negative, you're basically losing out on half of the information. So that's just something to consider. There is a subset of sentiment analysis that will tackle problems like this. It's sometimes referred to as target-based sentiment analysis. So if this is something you yourself want to tackle, maybe you could do a literature review on DBSA. Same thing with the category or similar thing. So this sentence does in fact refer to food, but it also refers to service. So maybe we want an approach where it's not just one tag, like it can be food, but it can't be any other. Maybe we want an approach where it can be food, but it could also potentially be service or value or whatever. So that would be multi-label classification might be one way to get around that. So just sort of having introduced you to these three tasks, NER, sentiment analysis, and classification, I wanted to highlight how review trackers data might be using these tasks. So this is an actual review for an actual company, came in through Google, food was good, et cetera, et cetera. So what we might call this is keyword extraction, but one way of thinking of it is as a type of NER, where if it's a keyword, if it's an important word, then it's a named entity, and otherwise it's not a named entity, it's not a keyword. So here, everything underlined has been extracted by our in-house model as a keyword. So food is a keyword, noise level is a keyword. Quiet is also a keyword because it's important, that's useful information to extract, but you'll also notice quiet as an adjective. In the previous example, maybe it wouldn't necessarily have extracted an adjective. So I also want to point out that even though before my example was like genre, music, game, it's really up to you how you slice and dice, how you define your NER tag set. So this is quite different from that previous example. Another very common NER tag set, if you're maybe processing like news text, might be a person's name, an organization name, or a location name. So then you can read through, let's say, all the New York Times for a given day and extract what you want to know about that. In the healthcare domain, they're going to have their own completely different NER tag set. So this is what we have here. So then the next step is applying sentiment analysis. So for each of these keywords, you can see it's underlined in green or red for its sentiment polarity. So food is good, keyword food is therefore positive, noise level is unbelievable, so noise level sentiment is negative. So this is, as you can see, target-based sentiment analysis because it's more fine-grained than just predicting it across the entire sentence. And then so finally, on top of that, for each of these keywords, there would also be a class predicted, right? So maybe food would be in the food category. Noise level might be in the sort of a category about the ambiance of the location, right? And so you can see that here, this sort of highlights actually all three, the keyword extraction, the sentiment analysis, and the classification all aggregated together. So this would actually be data, for a given location over a given time period, all the dimensions of the keyword. So maybe clean was mentioned positive 57 times, and that's in the atmosphere category, versus loud mentioned in 28 times, and that's negative sentiment. So you can see, like maybe if you were just looking at that, you would say, okay, maybe it's somehow performing NLP to get me this table that you see here. But under the hood, you could really break it down into these three tasks I outlined before. So I believe, yeah, that's all I had about my part of the presentation. I'll hand it over to Joey, and maybe we can take if there's any questions at the end.
Cool. Yeah, so I think one of the biggest things that we've run into while working with NLP is kind of managing how the models that we generate are stored and how we deploy them and how we test them. So I'm just going to go over that very quickly. So what we've kind of moved to now, before we actually had our models getting pulled down by S3 every single time we deployed, that was kind of getting unwieldy, and it was difficult to quickly push changes out because we'd have to pull down 3 gigs every time. So what we've done now is our models are still stored in S3. It makes it really easy to update by hand whenever Andrew has anything new for us to use. But what we do now is we have a Jenkins job that we'll grab from S3 and put them into essentially a Docker volume, we use Docker Swarm for managing our containers. So there's a plugin for that called Cloud Store. So we'll store those in Cloud Store and then attach them to our containers at runtime. So basically what ends up happening is they're all inside the file path for each container that needs any of the AI models. And it allows us to very, very easily, with the click of one job, swap our new models in and out in case anything goes wrong or if we need to change something. And it's really nice. And so testing is very, very simple for the most part. It's kind of what you'd expect. Model updates, we run through our integration test suite. It's nothing fancy, just typical integration test stuff. This is really nice. It's integration tests. It allows us we've had issues before where we've updated our models and our unit tests break and then our integration tests break because these updated models end up having significantly different values. Like occasionally you'd think it would take, an example of like, I hate the burger. The old model might have just taken burger and now the new model takes hate. And so we most of our stuff is just validating that our models still operate at least mostly the same. And we focus on our unit tests a little bit more to focus the granularity of ensuring our models are returning accurate data. That's all from me.
Okay, awesome. Are there any questions in the chat? While we're waiting for the chat to ask questions, I was wondering, how are you measuring these models and making sure that they are predicting what you think they should be predicting?
Sure. So for classification and sentiment analysis, you can just use straight up accuracy. So like, percentage predict. So actually, let me take a step back. So you train your model on this data set, but that's annotated, right? So like, let's say, at some point a human being went through and read a sentence, the burger was great, and said manually, that is positive sentiment, et cetera, et cetera. So you have this annotated data set. Maybe you take 80% of that to train on and 20% to test on. You can split it up differently with like a dev set as well. But regardless, so you have this sort of this series of inputs that the model has not seen before. It hasn't been trained on. And then you feed it and see what it predicts. And then you just compare its predictions to the sort of gold standard annotations made by a human, if that makes sense. So it's almost like grading a Scantron test. And so then for classification and sentiment analysis, like I was saying, you can just evaluate that on pure accuracy, percentage that it guessed correctly, that match with what the human said. And in theory, you could use accuracy for NER, but it's better to use something called F1 score because the system can kind of cheat the metric in almost like a stupid way. Like it could, it could guess every single word is a keyword, and then it will get 100% of the keywords correct, but it's also going to get you a lot of garbage. And so F1 score is just under the hood, it just balances out. Technically, it measures the recall and the precision. Yeah, so any sort of sequence labeling task like keyword extraction, NER is usually going to use F1 score.
Okay, awesome. Thank you. We do have a question in the chat from Harry Chin. Are the loaded models hot? Yeah.
So we actually currently have 3 classification models running in our categorization or classification container. And we haven't really had any issues. They're all 3 are always loaded